and thank you for giving us the opportunity to present some recent use case on passive monitoring of buildings. So very happy to be here with you today and to follow this agenda. And please interrupt me at any point if you have any questions. Don't wait until the end, and I will try to stop regularly in order to ask for questions and for interaction. So thank you again. So I would like to start, first of all, by saying a few words on passive monitoring of buildings. I will explain what it is and how do we do it. And then I will move to two projects, one associated to a direct application of the method. And the second project is basically the example of the assessment of a structural health in the context of a major earthquake. A little bit about Isamgeo. Isamgeo has been founded in 1995 in Germany and is now based in Italy since 2010, covering different activities across Europe. The expertise of this 15 people team is on geomodeling, work mechanics, geophysics, and software development. We have various clients across the oil and gas, mining, and as well partnership with the University of Padova, where Giorgio, the previous speaker, was coming from. So let's start. What is structural health monitoring? So it's basically the activity to monitor over time a structure, to understand any change in the material properties or any change in the geometry of the elements composing the structure. The reason we do that is because of the operation. A structure can degrade. It can degrade because of its age, but it can degrade as well due to its use. Some structure as well can be compromised by natural hazards like earthquakes, storm, strong wind. So it's important to understand how a structure would behave based on a dramatic change or displacement occurring on the ground of this structure. So some recent example, like for instance, last week, we have all seen this dramatic picture of in Taiwan, where earthquake of magnitude 7.4 hit Taiwan. And we have now pictures in our mind of building collapse, building as well tilted, but as well this Taipei building, right, very tall, yet who has been able to stand still thanks to a pendulum. So we can see that structures are not equal because of their structure, because the way they have been built, because of the elements which compose them, but also because of the interaction on the ground that they are being built on. And this, of course, have different type of consequences. Closer from us, we have Turkey. Turkey as well is a place where very active in terms of earthquakes. And there's a need, because of the energy distribution across Istanbul, there's a need to store gas, liquefied gas, on this spherical container. And this spherical container could be potential in threat during earthquakes. And here are some pictures where we can see, and we will see this on the presentation, where basically the braces here, I don't see it, maybe you see my mouse. You see that this metallic brace supporting the vertical columns tend to fail. And when they are failing, basically this column just bend and the entire container just drop. And this picture is quite interesting because you can see that one was holding still on the right while the other one just collapsed. So how do we analyze the operational mode of the building? We will see that basically we are combining measurements by measuring the acceleration of the velocity of the ground and of the structure. And by integrating these measurements together, we can compute the frequency response of the structure. From this, we can estimate some parameters. And here we will see that we are mostly concentrated on the frequency peak of the data. By observing this frequency peak and comparing those with the estimation made by the model, we can update or we can be sure of our model of a structure. And through the modeling of a structure, we can see which elements are more resistant, more compliant, and the one which may need some attention. Do you have any question at this stage? No? I will move to...
Okay.
Okay. So let's move to the first project. The first project is based on this spherical vessel, this tank. This data has been recorded in November. And what we put is only 4 instruments. We put 1 velocimeter here on the ground. And we put 3 accelerometers on the structure, 2 on the equator of the structure, and 1 on the top of it. And we measure for nearly 1 week this activity of this tank. Here are some pictures where we can see the spherical tank close by. We can see as well the column, which is basically supporting this big sphere. We can see as well here a small beam on which one of our instruments will be installed. And here we see the 2 braces supporting 2 out of the 12 columns. And on the top here, on this plate, another instrument was put. So let's look first at the measurements on the ground. By putting a sensor at the ground, the objective here is really to measure the input of a vibration to the structure, because there's some ambient noise. So let's make a parenthesis by noise. What is a noise? Here, noise can be seen as a signal as well, but we call it noise because it has not been created intentionally, okay? So, but it constitutes a vibrational input to the structure. And it's interesting to measure this noise, because maybe we could imagine that this noise is constant over time. That is not. So here we see the spectrum of a noise measured for 3 hours. The first 3 hours of a day, from 3 a.m. to 6 a.m. And what we see is on the 3 components, we see some correspondence on the peak, right? We see that the 3 components of these receivers are behaving somehow in the same way, meaning that we see some peaks, regular peaks. What we see still is that from a package of 3 hours, so here we are seeing 3 hours and decomposed by 1 hour. We see that over time, we see some increase of the amplitude. We still see the frequency peak at the same frequency, but we see some amplitude variation. And when we move from 3 o'clock a.m. to 6 a.m., what do we see is this amplitude start to amplify as well. Yet we see still the same frequency at the same frequency peak. but we can still see a difference in the amplitude. So this is quite informative. What we do as well to refine this ambient noise analysis is to, instead of looking at one spectrum of 1 hour, 2 hours, and so on, what we do is to compute an attribute of the data which summarizes the data every 15 minutes. How we do that? We take 30 minutes of data and we compute the mean square of the stack data, and we put it every 15 minutes. So it's a sliding window of 30 minutes every 15 minutes. So it helps us to understand the variation. And we have this kind of dashboard that I'm showing here. Here, you see 4 dashboards. One on the bottom left, you see the one which is on the ground. And then the 3 others are the accelerometer, which are on the structure. It's interesting. Why? First of all, you can see that the receiver here, this one, 47, which has been put on the top, has been working very well only for 1 day. So it's quite interesting, because when we deal with data, it's always important to understand the data completeness. And the data QC part of any type of data observation is really important. It's always going to this question, how complete our data is and how accurate our data. So here, this dashboard indicates that this receiver worked very well, but only for 1 day. The other information here that we see, which are across here on the 2 accelerometer on the equator of a sphere, show the same type of information. We see in the morning, in the night, low amplitude. As the activity on the site pick up, we start to pick up more amplitudes, not only on the site, but as well on this structure. When the activity stops, maybe for lunch break, then the activity stops. And in the afternoon as well. And then after the office hour, then we are back to this background level. It's also interesting to see and to know that from the 11th to the 30th November, there has been a decrease of the capacity of this tank, meaning the tank was filled by 80% and then dropped at 2% because people were taking the gas from this container. So you can start to see some indication of a type of activity associated to this building, to this structure, due to the activity inside the tank, but as well associated to its surrounding activity. So let's go a little bit further. What we have seen is that basically we see from this that there's some variation associated to the activity inside the tank, activity around the tank. Let's see if the movement that we are observing on the structure is the same on the both directions. The receiver that we put have the capacity to measure the displacement on 2 directions. Directions which is parallel to the structure, and one perpendicular to the structure. Okay. So the data in blue are the one which have been measured parallel to the structure, and in green, the one perpendicular to the structure. Again, what is interesting is that the displacement that these receivers are registering are not the same in terms of amplitude. Here you see that the parallel to the structure is systematically higher than the one perpendicular to the structure, and at different hour. So this is quite interesting. Now we know that there's a movement inside this structure, but the amplitude of a signal differ from the direction at which we are measuring these measurements. So this is interesting. What we see as well is that over time, when we have more activity on site and that the amplitudes increase, we are able to see as well this amplitude on the spectrum. And not only when we go from 6 to 9 hour local time, but as well from 9 to 12, we see suddenly a decrease and another pickup of the activity in the afternoon. So it looks like that there's an activity which makes this spherical container kind of breathing in and out. Let's go further as well on the decomposition of the frequency domain. Here you're looking at 4 components because we have 2 receivers. We are considering then the 2 components, so 4 components together, and we are decomposing the frequency. What we see that we have some different frequency, mostly between 1 and 2 hertz on one direction, and on the other direction we see some other amplitudes at higher frequency at 5 hertz, which are of lower amplitude. But what we will concentrate on are the highest amplitude at the lowest frequency. So here again, this spectrum is associated to the velocimeter on the ground, which we see the spectrum which presents some frequency peak. And here we see the results of a simulation where we have this peak of frequency and as well other frequencies which can be observed. When we compare the model results on the right with the observed results on the left, we start to see some correlation related to this peak really between 1 and 2 hertz, as we see here. So looking at this single value decomposition and the data, we see some correlation between what we observed on the data and this frequency domain decomposition, where we see a peak at 1.4 hertz. The question we asked is this mode or is this frequency peak always visible? And the answer is no. Unfortunately, when the tank, for instance, was full at 11% at this hour, which is between 4 and 5 o'clock, where the noise was relatively high, we were not able to see this peak. So when the noise level is relatively too high, it looks like that this mode is hidden. When an hour later, when the tank was full only by 2% and the noise level was decreasing, we were able to see again this peak. So it looked like that the noise, there's a limit on the noise floor, which makes us seeing this mode or not. When we waited for another hour, when the noise floor was lower, we were not able anymore to see this peak as we thought. And our explanation is that the energy of the vibration at that time is not sufficient to trigger the mode. Why? Because after this activity hour, there's not enough ambient noise to create this input signal to the structure and to make it vibrate at this frequency. So what we see is that there's a kind of trade-off between ambient noise to be high enough to excite the structure, but yet not too high noise level would mask this oscillation peak. So let's see on the modeling side. So to model the structure is quite complex, meaning that it's composed of different elements. And here there's a choice. We are not going to measure every single element of this body. We are going to simplify it and how we simplified it, we consider the model with 12 columns, okay, with a certain height. We consider all these braces, which are basically linking these columns. And we considered, instead of this big sphere, we considered a lump mass based at the center of a rigid diaphragm. So a kind of a plate, if you want, but it's more flexible than a plate. It's really a diaphragm. So with some rigidity based on the top of this column. So basically the way to make this structure, which looks complex, to simplify it with 12 columns with braces and a diaphragm on which we put a lump mass. This lump mass is able to move in 3 degrees of freedom on the 2 horizontal axes, and as well with a rotation around the vertical axis. Okay. And we made as well some further assumptions associated to the modeling aspect as well. When we did the modeling, the results of the modeling has been that we observed for the same capacity of tank filling, which is 2%, we observed frequency at 1.4, which is, and this corresponds to what we observe here on the data. So this small project has been quite interesting for us because it's a way to illustrate the fact that we can use ambient noise as input to understand how a structure can vibrate. What we observe is that this vibration mode is not always visible. It needs a surrounding activity high enough to generate vibration on the structure. However, we need to be careful that too high noise level could mask this peak, because this peak is not of too high amplitude. However, there's a good match on the observed and the modeled, which are on the frequency that has been modeled. What we did as well was to check how this frequency of the oscillation on the first mode would behave as the tank is filled, meaning that here we observe 2% when the 1.4% hertz when the tank was filled at 2%, which correspond to the modeling. However, if we fill the tank, then this frequency would go at a lower frequency. And this is also maybe one of the reasons we were not able to see it when the tank was filled. And another also explanation is that when the tank, we were able to see the tank getting empty. We were not able to measure when the tank was getting filled. So a potential future project could be to monitor the complete cycle, and I would say complete several cycles of tank filling and tank emptying in order to see the variation of this peak, where we would be able maybe to see it going a little bit at a lower frequency as the tank would fill, and going up at a slightly higher frequency when the tank would be emptying again. This concludes the first project that I wanted to share with you. Let's see if you have any questions, because I would like to move to the second project where we assess the health structure for major earthquake.
So I have some questions, but maybe the doctoral candidate have some questions.
Because they are across Istanbul, and critical because they are industrial buildings which basically compress or decompress gas for the use of people around. We monitor 20 buildings on 9 sites. 3 sites were on the Asian side and 6 on the European side. And these buildings were separated or categorized in two ways. Administrative one, which is basically this kind of building here, which is a square type of building, which is quite strategic because this is where there are all the commands of stopping, closing, or opening valves in order to stop the flow of gas. And inside this RMS building, we are calling them RMS building. Don't ask me what the acronym is for, but this building is basically composed of all the instruments of the operations needs to distribute and to compress the gas. So here you can see that some pipes are coming in, some pipes are going out. These buildings are usually made at some point by internal anti-blast wall in order to separate the building and protect one part of the building if there's a type of an explosion. We use for this monitoring 17 receivers, 2 velocimeter, and 15 accelerometer. And usually we put inside these industrial buildings 2 accelerometer inside the buildings on the steel frame, and the other instruments were put outside on the concrete wall. So we follow the same process as before. We did ambient noise analysis and power spectral and density analysis, the operation model analysis, and then we compare it with the results on the modeling side. So let's take one example that has been recorded from October, over 1 week, basically, with one on the ground and the other 6 across the building. Here you recognize this ambient noise dashboard that we put for different type of days. So from the 22nd of October to the 27th of October. This is a nice example where we can see that we have basically lower amplitude during the night, ramping up of the activity, breaking over the break, and so on. And here, this blue and gray are on Sunday, where the activity on the site was lower. So coming back to the data analysis, we can see that on the power spectra, we start to see some peaks as well on the different components. Looking at the frequency domain decomposition to understand on which direction the movement tends to be, it seems that there's more movement on the transverse direction of the building at lower frequency, but this graph is relatively difficult to interpret because there are many peaks for this specific building. When we started the modeling, we took into account all the structure that was made available for us at that time. We consider the beams as this metal frame on the rooftop and across the columns which are in red. For the finite element modeling, we constitute then all these elements, so to create this model for the entire building. And we separated 2 parts. The part associated to the metal part of the building, which is in blue here, and the other one, which is associated to this reinforced building, including the anti-blast wall, which is basically touching this part of the building. So 2 buildings, 2 parts of the building. Through the finite element modeling, this time we didn't have, like for the spherical tank container, one frequency only. We had a series of frequency peaks, which are modeled based on the movement of a mass on the longitudinal direction of a building and on the transverse direction of a building. When we compare this frequency with the spectrum of the data, we see some correspondence, meaning that all the modeled frequency or most of the frequency which were modeled were found on the data. Not all of them above. What was interesting here in this graph is that the spectrum on the picked up by the receivers inside the building were here. And you can see that the spectrum have a different type of behavior than the one measured by the receivers on the outside. So these 4 receivers are measuring outside, and you can see more similarity on the terms of the look of the spectrum than on the other one. So why this is important because it reassures us that we should consider 2 parts of this building, because these 2 parts of the building oscillate in a different way. Why? Because again, they are built in a different way. One is made by steel, the other one is made by reinforced concrete. One includes this anti-blast wall, which basically make it maybe more rigid than the other one. So the reason why we did this is to try to answer the question, what would happen to this building if a major earthquake occur? So taking the hazard map of Turkey for this specific site, we extracted the lateral elastic design spectra, which basically indicate the gravity and the acceleration for this type of period, for this type of earthquake. So we are considering 4 types of earthquake, DD1, DD2, DD3, and DD4, based on the probability of accidents in 50 years and their return period. And what is expected in Istanbul is between DD1 and DD2 earthquake. Through this modeling exercise, what we have is we superpose this spectrum that we extracted. So here, this 3 first spectrum are the spectrum here that you see for 3, 2, and 1 type of earthquake with different type of growing amplitude. And against it, we put the capacity curve that was estimated for this part of the building. So for the metal part of this building, we have capacity curve, which are basically exceeding the lateral elastic design spectrum. So what does it mean? It means that here for this part of the building made of metal, the building will be able to stand and or remain intact in case of major earthquake. However, for the part associated to the reinforced concrete, here again, this 3 colored curve are the same as previously. You see it on another scale. But here, the capacity curve for this part of this building is lower. And as a consequence, there will be some parts of the building here which would be damaged. And there's a good peak ground acceleration which is estimated for considering the interpretation of this spectrum. So this itself is quite interesting. Two further type of the modeling also include, because we included different type of elements, we are able to understand then where and the type of failure which could happen at this part of the building. So all this information are provided to civil engineers, which are able then to understand how to define plans in order to protect better this part of the building. So This is what I wanted to provide you as a second example of this type of study. Do you have any question?
I have a small question. What finite element modeling software do you use? Type of building.
Yeah, that's a good question. I don't have a name myself. It was one of my colleagues who did it. And yeah, I shouldn't know it. I don't have it here
It's fine.
with me. Thanks for the question. Next time I will have it.
It's fine.
For me, I would like to ask, how do you choose the sensor position?
That's a super question.
There is a pre-modeling before, or,
Yeah, that's a really nice question. And so I think to answer, so it has been made by, so the criteria has been to have sensors inside and outside. And inside, I think it was made associated to the frame and to the accessibility. So they were able to put it on the steel of frame inside, and I can hear some noise. I wonder if someone wants to talk. But what and then they did it from the first building, and then they started to use the same and apply the same methodology on all the buildings. And then for the outside, it was basically on the outside, on the corner. With the idea here was to make sure that they can record at the corner, because they thought, or we thought, that the oscillation would be larger at the corner, and here in the middle, because it's close to the anti-blast wall. However, your question is really, really good, because ideally, I think we should have, I mean, I would have liked to do an experimentation where I would put sensors inside and outside nearly at the same level. This would have been quite interesting as well. As well, I would have liked to put some sensors underground and high on the structure. Why? Because the higher you put the sensors, the more vibration you see. And this, unfortunately, for this choice, has been put on the same height. But it would have been also interesting to look at the variation of a vibration across the structure on the height.
Nadine, you have raised your hand.
Yes, basically, in one of the slides, you say that you could not measure all of the modes. You match them up, right? That's the theoretical with experimental, right?
Yeah. You
Yeah, that one. Yes.
one? Yeah.
Yeah. So when matching them up, do you use like the mode shapes, or how do you match the observed to the modeled ones?
That's a really good question. Thanks for this. And you're right. I looked at the pic, but only it's really first analysis. But what would be very interesting would be, as you see, the pics are of different shape. So it would be, I'm sure there's some information here which could be extracted more than just.
So thank you again for your lecture, and so I will stop the record. I will have to cut